Hello and welcome to this STA virtual conference presentation on pool water treatment optimisation. I'm Andrew Gaffey and I've worked on the technical side of the pool industry for over 35 years, involved in water treatment. I work as a technical trainer providing training services to pool plant operators and service engineers, and I also provide consultancy services for water treatment. My presentation today covers some aspects of water treatment which I feel will become increasingly more important as we drive to try and reduce energy and carbon emissions. At the end of this presentation, I'll be pleased to stay around for any comments or questions that you have, and I hope you find the presentation useful. So without further ado, I'd like to move on to the first slide. Energy in the swimming pools. So indoor swimming pools are the highest energy consumers of all building types when you consider the unit of area. Why is that? Well, there are large volumes of air and water at higher temperatures, and this is needed, of course, to provide bather comfort. There are large wet and dry surface areas through which heat can be lost. For example, there's heat loss through evaporation, radiation, and ventilation. And there's also a high consumption of water. A lot of that water is cold water being used for the pool water treatment system. There's also hot water distribution systems and generally a large number of electrical pumps required to keep the building operational. Also considering that this is not the type of building where you can just switch off at the end of the day. The water treatment processes must remain running to avoid deterioration of the pool water and also protect the building fabric. So for the reasons we've just covered, there are lots of opportunities for energy conservation in swimming pools. And this ranges from the construction materials and insulation of the building through to the recovery of heat from air and water waste, hydraulic efficiency of the pumping systems and water distribution, and also water heating and circulation pump efficiency. But one of the areas I think which is overlooked a little is the actual design of the filter system and the efficiency of the water treatment regime itself. And sometimes I think it's underappreciated just what an impact that has on the rest of the facility operation. One of the most basic observations you can make to determine water quality in a swimming pool is to actually look at the pool water. And it's quite true to say that for most pools, if you stand on the pool side and look into the water, most pools will appear to have pretty good water quality. But when you look through the length of the pool, that is the real test of the quality of the water. And if you can't see end to end in your swimming pool, in almost perfect clarity, then there's certainly room for improvement in the water treatment system. And really that cloudiness that you see is caused by suspended particles in the water reflecting light, and that's known as the Tyndall effect. So you can see in this pool here it's quite an extreme example, but there's certainly a lot of room for improvement in water quality. So it's fair to say that most of the pollution in the pool cannot be removed by filtration alone. In fact, most of the nuisance pollution is much smaller than a filter can possibly handle. So we have to look at other treatment methods to achieve the correct quality of pool water. So what happens if these suspended particles are not removed and they continue to circulate in the system? Then the water becomes heavily loaded with organic material, and that basically reacts with chlorine to produce combined chlorine. And therefore, if you need more chlorine, if there's more chlorine demand, you'll therefore need higher levels of pH correction. So you end up with a lot more chemicals being used. Organics react with chlorine to create a range of disinfection byproducts, and some of these are more harmful than others. Some of these include nitrogen trichloride and trihalomethanes, or THMs. So volatile byproducts such as THMs, which is mainly composed of chloroform, can be harmful to pool staff and regular competitive swimmers. And if you consider that staff are on the pool side for several hours per day, or competitive swimmers may be swimming for a couple of hours in the morning and a couple of hours in the evening, they have quite a lot of exposure to these byproducts. So we really need to consider their health and well-being when we are designing pool water treatment systems. So these chlorination byproducts can also have an effect on air quality and on the fabric of the building itself. THMs and nitrogen trichloride leave the pool water, hydrolyze in the atmosphere to form weak hydrochloric acid, and this hydrochloric acid then deposits itself on the building fabric, especially on colder steelwork, things like that, and it dries out and degrades into sodium chloride. So these sodium chloride or salt deposits can build up over time and cause quite catastrophic damage to steelwork, or a lot of corrosion at least. And there have been a number of incidents across the world now where there have been serious incidents in swimming pools and leisure centres where ceiling structures have collapsed or HVAC systems have collapsed. And this is one example in the UK here. So it's a very important point to consider, and it just demonstrates how water quality also has a huge impact on air quality and the lifespan of the building. So what are the options for controlling chloramines in swimming pools? Well, the go-to options for many pool operators over the last couple of decades has been to use UV and ozone systems. But there are penalties involved with using those technologies. One of the penalties is its chlorine consumption. In UV systems, that's caused by the effects of UV radiation on chlorine, and which chlorine is sensitive to. And in ozone systems, it's caused by absorption through activated carbon, which is also used to remove ozone from the water before it's returned to the pool. So there are those considerations. In any case, UV does rely to some extent on good water quality in the first place in order to minimise fouling of the quartz sleeves inside the UV system. I was only talking to some engineers a couple of weeks ago who said, it is becoming a particular problem in poorly filtered pools, and that UV systems require a lot more maintenance. So what are the choices? Is it to use energy consuming UV or ozone treatments to continually treat a chloramine problem, or is it better to optimise the filtration to reduce the sources of chloramine formation in the first place? And that really is the point of this presentation, and basically saying that shouldn't we focus on getting the basics right first, which is to produce good quality filtration, a well-designed system which is enhanced by flocculation, and we'll talk about flocculation in a bit more detail. To have an efficient pool water treatment system, it's important that we understand the type of pollution that's entering the pool and how best to deal with it. So firstly, we need to be able to classify these pollutants into certain groups, and then we can decide how to treat the individual groups, how best to treat those groups, and what technology to use to do that. So firstly, undissolved and suspended particles in the pool water, such as soil and sediments and lint from bathers, things like that, that can be fairly easily dealt with by most pool filters. Colloidal substances are a little bit more of a challenge. These are large molecules or submicron particles distributed in another substance, like mucus and algae. And then finally, dissolved substances which can't be removed by filtration. And these can be organic and inorganic chemicals and salts. And flocculation can be used to remove some of those substances. Some of them also remain in the pool and have to be simply dealt with by freshwater dilution. So we have a range of treatment options. to deal with the pollution that enters the pool. So if you look in the left-hand column, you can see that we've got the various groups of pollutants and bacteria and protozoa, and then we've got the filtration flocculation column, and you can see that that column ticks almost all the boxes and can deal with a wide range of pollutants compared to sand filtration only, which is pretty poor. So we have to consider, if you look at the oxidation column, if we don't apply enough of the other treatments, that will give chlorine the opportunity to react with virtually every type of pollutant that enters the pool, and that's where high combined chlorine levels come from. So we really want to minimise the amount of pollution in the pool before we start to apply chlorine for oxidation and disinfection. UV radiation does have some benefits on dealing with protozoa, but for bacteria it's not so effective, because if you consider in a chlorinated swimming pool, the bacteria should be dead and dealt with long before it gets a chance to get back to the UV treatment system in the plant room. UV also has some limited effects on dissolved substances, and some of those can lead to reactions that are undesirable. So really we want to limit the use of oxidation, UV radiation, and use the other technologies to try and clean up the pool water. So really we want to apply an efficient flocculation filtration system, and to reduce chlorine to doing a few basic functions and much less of the oxidation workload. So this slide is a graphical representation of what we've just been saying, and it's important to note that chlorine is a good disinfectant, but it's not an ideal oxidizer because of the fact that it reacts with almost everything in the pool water. So again, reducing the workload for chlorine is very important if we want to reduce the combined chlorine levels in the pool, and also to try and minimise the amount of fresh water we need to use to control that problem as well. I think it's important to appreciate the scale of the task that the pool filter has to perform. When you consider, if you look at the graphics here, and these sand grains in the pool filter are about 0.5 millimetre in size, and for comparison, the size of colloidal substances can be 1/1000th to 0.1 of a micron. It's incredibly small, and to ask a filter to capture these particles is almost impossible, or it is impossible, without some additional assistance. So the flocculation process really is intended to collect and bond together these minute particles into much bigger filterable particles, and by adding a coagulant we can destabilize the charge of these particles and cause them to attract together into much larger chains, which can be captured by these sand grains. Most of the pollution in pool water carries a negative charge, a negative surface charge, and those particles are just floating around freely in the pool. But introducing a cationic coagulant such as PAC, it introduces a positive charge and destabilizes these particles and causes them to cling together. And when they begin to cling together, that's called the microfloc process. So this happens fairly quickly before the pool filter, and then when these microflocs enter the pool filter, the headspace inside the filter allows calmer conditions for these microflocs to grow into macroflocs. These are much larger chains of particles which can then be easily removed by filtration. Filtration flocculation methods. What has improved? So for anybody that's been around the pool industry perhaps for more than 20 years will remember that the main way of coagulating swimming pool water was to add large amounts of aluminium sulfate into a strainer basket, which would be inserted into the circulation system just before the circulation pump. And it's fair to say that many pools were probably grossly overdosed with aluminium sulfate. But over the last 10 years or so, there's been an awful lot of research into filtration and flocculation, and we now have a really good understanding of how this process works. And in response to that, and in response to national regulations and standards in some European countries, and particularly Austria, Germany and Switzerland, many filter manufacturers have responded and really made some improvements in their filtration products. And it just seems to me that the UK pool industry has perhaps lost its way a little bit during this period, and doesn't really seem to have progressed in its approach to filtration system design, and yet it's by far the most common method used in swimming pools, and still probably the most affordable method. So over the next few slides we'll look at filter design and practices in the UK compared with Germany, Switzerland and Austria, for example. So if we look at the German DIN standard, which is the Deutsche Industrial Norm, there are a set of standards for pool filters that must be satisfied for use in public pools. The filter design really is critical to provide the ideal conditions for efficient flocculation to occur. So let's just look at some of these designs and some of the advantages and flaws. Some of the most basic filters available on the market, which you might class as being a budget filter, use lateral collector systems with a gravel support base. When the inlet water enters the filter, it's got a fairly tight headspace. So what tends to happen is that the water is deflected from the roof of the filter around the sides, and this causes piling of the filter surface, or at least an uneven filter bed. Water then takes the path of least resistance through that filter, and some areas of the filter become heavily contaminated or even compacted over time. So basically you've got an uneven filtration area or a reduced filtration area resulting from this. The collector systems on these filters, because they're mounted on a gravel bed, tend to move over time, and if they don't stay level you can get uneven backwash flow. So in other words, some areas of the filter may remain dirty after backwashing. These type of collectors are usually not suitable for use with air scour compressors. So again, it's a bit of a disadvantage because air scouring can be very beneficial prior to backwashing. In this design as well, the gravel media below the laterals doesn't receive much chlorinated water, and the lateral area underneath particularly becomes quite heavily contaminated, and there have been several reports of filters becoming grossly contaminated in this section of the filter. One advancement on this basic design of a lateral collector filter is to use a concrete base. So this concrete base avoids the contamination issues that exist with gravel bases, and it also helps to keep the laterals fairly flat. But this type of filter again usually has a very low headspace, so it still has the disadvantages of uneven filter surface areas. Now if we compare this to filters that are generally constructed to the DIN standard, you can see that the headspace inside that filter is much larger, and the inlet water is usually diffused through several inlet arms inside the filter, or through a diffuser hat similar to which is shown in this diagram. And the collector system is composed of nozzles, and these are like slotted cups, finely slotted cups, which can efficiently collect the water with very low head loss, and also act as a good tool for air scouring prior to backwash. Again, air scouring is important really because it pulverizes the sand with air, in effect stirring up the filter bed to release dirt from the sand prior to the backwash. So looking at the design of the DIN filter in a little bit more detail, you can see that the space above the sand in this filter is basically divided into two different spaces. If you like, there's the head space, which is above the inlet diffuser, and then there is the freeboard height above the sand level to the backwash water collector, or the tundish. So all this space serves to provide time for the flocculation process to occur. So the diffuser is there to create calm conditions in the filter. The head space is there to prevent the water deflecting round the sides of the filter and causing piling of the filter bed. So all these features here are really important for efficient flocculation. Also, the freeboard area is important during backwashing, because if the backwash speed is correct, then the filter bed should expand by at least 10% during a backwash. So this space is needed to prevent sand from being ejected from the filter during backwash. Also, this design of filter is intended to house several grades of filter sand. So there'll be a coarse sand, a fine sand, and both these are placed on top of a gravel support bed, which is then directly above the nozzle plate. So we'll look at some of the additional features that many manufacturers are now adding to these filters in excess of the DIN requirements. So all DIN standard filters include a large air release connection on top of the filter, and this is really just a convenience to allow quick evacuation or flooding of the filter after backwashing. These type of filters either include an inlet diffuser like this one, or perhaps multiple inlet arm spreaders, again just to make sure that calm conditions exist in the top of the filter to allow the flocculation process to complete properly. Inspection windows are mandatory on all DIN filters, but to be honest are pretty useless unless a spotlight is installed. So many manufacturers now include a spotlight. This makes the inspection window much more useful because the operator can inspect the filter surface every day. You can check that the filter surface is flat, you can check that the expansion is working during backwash. So a very useful feature. The backwash line on a DIN filter is larger than the water outlet. And the reason for this is that the outlet serves obviously as a backwash line. So these filters are required to backwash to gravity. So there's no pressure inside the filter during the backwash, which probably sounds quite surprising to some people in the UK. But yes, this is the standard in Germany and Austria and Switzerland. So for that to occur, you need a nozzle plate really that is capable of taking quite high backwash speeds. So for example, 40 cubic meters per square meter per hour is quite common as a backwash speed, and this ensures that the sand bed expands properly during backwashing and can release all the dirt. Some manufacturers also now include an access hatch under the nozzle plate, so this allows for quick repairs to be completed. Now the nozzles are usually designed with a life expectancy of more than 10 years, but if one or two of them were to fail after that time, they can be usually easily replaced without having to empty the entire filter vessel. So some useful additional features on some of these filters. So here I've included a couple of video clips just to show how useful the viewing window can be. And as you can see in this clip, this is the air scour section of the backwash procedure. In this video you can see after backwashing, you can see how the velocity inside the filter is reduced by the large diameter of the inlet pipe and the tundish, and you can see that the bed remains nice and flat. If you have a filter with a good viewing window and a strong spotlight installed, you can actually view macroflux forming in the top of the filter. Now, if you were to speak to an industrial process engineer, they'd probably tell you that for macroflux formation to fully develop, a time period of about 15 to 20 minutes is required. But in the pool industry, we just don't have that time. But we know that a period of at least 60 seconds will allow a reasonable time for macroflux to develop. So just imagine if you can increase that with a little extra headspace in the filter to an extra minute or so, then the efficiency of that filter can be greatly extended. So let's look at an example of a 25 metre pool with 166 cubic metres an hour flow rate with two filters installed. So if we take the 166 cubic metres an hour and divide it by 60 minutes, we get 2.76 cubic metres of volume. Divided by two filters means 1.38 cubic metres of volume available in each filter as an absolute minimum to give the 60 seconds residence time. So really we want to be aiming for more than that, and probably 2 minutes would be a really good target. Let's take a look at the wider aspects of the flocculation process. So you can see in this diagram that the circulation pump is installed, and soon after that there is a sample point for the pool controller to take water. Then on the outlet line of the filter we've got hypochlorite injection points, acid injection points, obviously properly spaced. And it's important for flocculation to occur that the hypochlorite injection is carried out after the filtration, because if we were to inject hypochlorite before the filter, it would rapidly change the chemistry of the water inside the filter. And we'll cover the water chemistry in a little bit more detail later on. So once we inject PAC coagulant, we're looking for that coagulant to be dispersed very, very rapidly. And ideally to do this, there should be a static mixer installed in the line, or there needs to be enough turbulence above the circulation pump to ensure that this coagulant can be dispersed quickly. The rest of the time then is basically for the formation of microflux before the water enters the filter. And then inside the filter, obviously we want the calm conditions for these macroflux to form properly before they hit the filter bed. And this is important because we don't want short residence time, because this means that the flocculation process could occur in the filter bed. We want to avoid that. We want to avoid the sand bed becoming contaminated with flocculant throughout its depth. So in a good process, most of the debris and dirt from the flocculation process should be held in perhaps the top 50 millimeters of the filter bed. For dosing coagulants, we really need to look at using very, very small output and very precise dosing pumps. If we pump too much coagulant, it could damage the filter bed, and if we don't dose enough, it's not going to be effective. So it's really important to get an accurate dosing pump. And also in line with PUTAG recommendations, it really should have continuous output. So pumps that dose intermittently are really not suitable for this purpose. The polyaluminium chloride used should be a food grade, which is clean and virtually clear with no particles, and that's usually typically contains 10% aluminium. So in addition to correct filter design, it's also really important to maintain optimal water chemistry for flocculation to occur. So in swimming pools, this means a pH of 7 to 7.4, a total alkalinity of more than 80 milligrams per litre. The other important points to consider are what you use to clean the pool surrounds on the overflow channels and things like that. You really need to avoid using anything that's surfactant based near the pool water, because these surfactants completely destroy the flocculation process. So be very careful what you select when you're cleaning pool decks. Also, to avoid using what we would sometimes call environmentally friendly cleaners. Perhaps these might be citric acid based cleaners, for example, and they can produce a lot of chloramines because they're organic acids, and organic acids also produce THMs. So these are two really troublesome types of products that can damage pool water quality. So moving on, what are the rewards of getting this flocculation process right? Well, the first one is a very visible result, which is amazing end-to-end water clarity. So you should be able to see right through the length of your pool in great detail. And this is obviously a nice result for clients using the pool. Because we've removed all of this debris from the water, you'll find that you get a lower chlorine consumption, and savings of 10 to 50% on chlorine consumption are quite common. Reduced pH correction demand also, because we're adding less caustic chlorine to the water, then you'll need a lot less pH correction as well. So this results in lower TDS, of course, because you're not adding as many chemicals, a lower combined chlorine, and also improved pool odour, because the chlorine is having to do much less work. The flocculation process also provides much greater protection against cryptosporidium contamination, so that's a really important benefit, and the filter can be really effective at removing that. Also, there's a lower risk of biofilm and algae formation as well, because most of the nutrients are being removed from the water progressively. So that's a big benefit for anybody that perhaps suffers from algae formation. It's usually because there's too many nutrients in the pool. By improving water quality, you can make quite a profound impact on the pool hall air quality as well, with a lot less potential for corrosion, which also means if the air quality is better, there's a lot more opportunity for reducing fresh air intake. So if you consider certainly countries that are with cold climates, for example, Canada and Northern Europe, it costs a great deal of money to heat up cold air. So if we don't have to exchange as much fresh air because the quality of the pool hall air is much better, then this can save a great deal of money, and also a great deal of carbon emissions too. Lower combined chlorine levels means there's less reliance as well on consuming energy consuming UV or ozone treatments. So these treatments can be reduced, again saving energy and carbon emissions. Less chlorine and pH correction chemicals also gives cost savings, relies on less plastics because you're using fewer chemicals, and also fewer delivery vehicle journeys. So it's really important when considering your water treatment regime, the wider impacts that it has on emissions. So it's not just the direct emissions from the building, it's the indirect carbon emissions as well that are very important, and that's going to be vital really going forward and contributing to the worldwide goal of carbon neutrality. Of course, there are other opportunities as well that exist when looking at refurbishing or installing a new filtration system from scratch, and that is to look at the opportunity for having larger filtration area. So again, it gives more time for the flocculation process to occur. Filtration speed is lower, which means reduced head loss as well in the system. There's less friction in the system, and you also get a better water quality filtrate as well. It's possible as well to lower head loss just by optimizing the layout of the plant room and the the design of the pipework. So for example, designing a system that uses wide radius bends instead of elbows, for example, it's quite easy to realise friction losses, 20 to 30% lower friction losses. Yes, this does mean a higher initial investment, but you've got to consider that the savings in energy and emissions last for the lifetime of that plant, so they can be very, very considerable. It's also important for engineers and pool designers to make sure that they size circulation pumps and plant for the pool to the best of their ability. If you look at some recent information from the British Pump Manufacturers Association, they published information showing that pump systems account for nearly 20% of the world's electrical energy demand, which is quite surprising. And pumps are the single largest user of electricity within industry. And across Europe, this annually accounts for over 65 million tonnes of CO2. But the more concerning point is that 80% of pumps that are installed are generally 20 to 30% oversized, and that the great majority of pump systems are not designed with energy conservation as a major consideration. So, for example, I think that means that most pumps are probably purchased based on price and not specifically efficiency. So this is something that will no doubt change in the future as industrial standards are tightened to try and reduce carbon emissions. And finally, I'd just like to add a few of my thoughts on sand filtration. And there are, of course, other filtration technologies emerging, and we haven't had enough time really to cover those today, but some of them do look promising, but yet some of them still need time to assess and to see how energy efficient or carbon neutral they truly are. Sand filtration is viewed by some as being old technology. That's quite true, and it is old technology. It's been around for over 100 years, and it's actually quite well proven. But I do feel it could be applied with some science to much better effect. It's probably the simplest and most passive filtration method available. Sand is an abundant natural product, and in pool applications, sand doesn't really wear out. It's made of silica quartz, which is one of the hardest substances known to man, but it does get dirty, so it needs to be cleaned occasionally. So in the long run, it is, as I say, it's quite an economical and passive technology, but it just requires a bit of extra space in the plant room and a bit more investment. But maybe these are the things we need to think about for the future. That concludes my presentation for today, and I hope you found it interesting, useful, or at least thought-provoking. And I'd just like to leave you with a comment by Professor Regina Sommer at the recent PUTAG virtual conference, when she said, "Optimisation potential for the future lies in flocculation filtration technology." And that's something I would certainly agree with. Thank you for your attention and for coming on board with the STA conference today, and I look forward to any of your comments and questions, and I'll be around for a while after this presentation.